Okay, so we are ready for the final talk of today. So it's a pleasure to introduce Benjamin. But before we give him the word, I just want to remind you that if you have suggestions for topics for the brainstorm sessions tomorrow, please send them to Frey. Yeah. So now we are ready. So Benjamin, please take the word. So you are going to talk about hard problems for isogeny-based cryptography.
Thank you. Indeed, I'm going to talk about hard problems for isogeny-based cryptography. Everything else today was about breaking cryptography, but some things are still hard. At least we hope they are. And I'm going to try and give you a picture of what still is hard and what can be built from that. And it's getting a little bit late, so I hope I'm going to keep the talk kind of light so you're able to follow without falling asleep. First, a little introduction to the question I'm trying to tackle. Looking at the audience, you're all familiar already with isogeny-based cryptography, but what precisely is isogeny-based cryptography? It's cryptography whose security relates to the difficulty of some isogeny problems. So a typical isogeny problem is this problem here. I'm given two elliptic curves, E and F, and I'm asking, can I find an isogeny between E and F? And isogeny-based cryptography is looking for protocols whose security is equivalent to this problem. And that problem, we suppose, is hard even for quantum computers. And then we get post-quantum cryptography. So that's the ideal situation. What is the actual situation? We do have upper bounds for essentially all isogeny-based cryptography. We know that most protocols, maybe all protocols, are provably broken if you can solve this problem over there. Given an elliptic curve, can you find all the endomorphisms of this elliptic curve? This is an upper bound on the security. If you can break that, you can break everything. But it's not quite the most interesting direction. What we're looking for is security proofs. What are the problems that if we assume they are hard, then the systems are secure? And then the situation is a little bit messy. We have a lot of different problems, mostly problems that depend on what schemes you're looking at. And some of them look very ad hoc. They look like your problem is just break the scheme. And then you can, of course, prove that your problem is as difficult as breaking the scheme. So there are a few good examples. Let's start with the best ones. The CGL hash functions, for instance, for Charles Goren and Lauter. The pre-image resistance of this hash function is provably as hard as the isogeny problem, the one where you're given two elliptic curves and you find an isogeny between them. So that's a pretty good example. It's not the only one. We even know how to build signatures from this problem. GPS signatures from Galbraith, Petit, and Silva have resistance to forgery that is provably as good as this isogeny problem. Now let's enter the world of weirder variants. For instance, ski sign. Well, ski sign is weird for many reasons, but one of them is the soundness, which is provably as good as the one endomorphism problem. The upper bound here asks to find all the endomorphisms of a curve, and this one asks you to find just one, well, a non-trivial one. You don't want just a scalar multiplication. So it seems that it could be a simpler problem. Then we have problems that feel even more remote from this isogeny problem, like the vectorization problem, which is the lower bound for the CSIDH key recovery. And then we can have even weirder problem like CSSI, whose security, well, whose hardness implies the security of CSIDH. But, well, the problem was a little bit too weird and turned out to be actually solvable in polynomial time, so that lower bound meant nothing. And in fact, the scheme is broken. Okay, so in this talk, I'm going to try and, well, first present definitions of all these problems, more rigorous definitions, the endomorphism ring problem, the isogeny problem, which exactly are these problems that I'm talking about, and try to build a hierarchy between these problems, which are harder, simpler, are there some that we can still feel are really secure, and what kind of crypto systems can we build out of them? So first, let's focus on the endomorphism ring problem. I'm going to try not to bore you, even though it looks like you're all mostly experts in this area. So I'm going to go pretty fast on what is the endomorphism ring problem. First, an endomorphism is just an isogeny from a curve to itself. And we talk about the endomorphism ring problem because if you fix the curve and look at all the endomorphisms together, they form what we call a ring. You have an addition given by pointwise addition and multiplication given by composition. And you may ask, what is the structure of this ring? What does it look like? First thing you may notice is that it's a ring that contains the ring of integers. It's not exactly a containment, it's an embedding. You can think of 1 as the identity, 2 as point doubling, 3 as point tripling, -1 as negation. So the ring of integers is essentially a subring of the ring of endomorphisms. That's already non-trivial information. It tells you that the ring is infinite, but it's not much. We know much more. If we just focus on the additive structure of the endomorphism ring, what we have is a lattice. And we know that it's either of dimension 2 or 4. We always work in positive characteristic. So a lattice, really in the sense of a Euclidean lattice, it's a geometric structure, discrete points in a vector space. So you would have an origin and maybe a basis here in blue. And the fact that Z is a subring of the endomorphism ring really means that you have a one-dimensional sublattice that corresponds to scalar multiplication. Okay, so this would be an example in dimension 2, but the example we actually care about is the dimension 4, which is essentially the definition of supersingularity. Your curve is supersingular if and only if this ring is a lattice of dimension 4. Okay, a quick example. We've seen this example already today. It's the prototypical example of a supersingular elliptic curve, and we know how to compute its endomorphism ring. How would you do that? So let's suppose that P is 3 mod 4, and that's going to be very important because otherwise the curve is not even supersingular. And we can try and ask, okay, we have this formula for the elliptic curve. What is the endomorphism ring? And if we can compute the endomorphism ring, we can even prove that the curve is supersingular. Maybe we find a ring of dimension 4. So we don't have very clever ideas on how to compute endomorphism rings. All algorithms are essentially, just look at it, try to find endomorphisms and see what you're finding. And if you are lucky enough, you're going to generate everything else. So here we have a fairly simple equation, and we can exploit that to find endomorphisms that are so simple you can just find them by looking at it. The first thing you might notice is that the equation is defined over Fp. Therefore, you have the Frobenius, the map that sends the point xy to the point x to the py to the p. It's not completely obvious that this is a new endomorphism, actually. Maybe this is just a scalar multiplication in disguise. But so how could you check that this is actually a new endomorphism? You could try and check how this behaves multiplicatively, and maybe deduce that it cannot behave like an integer, so it must be something new. To see how it behaves multiplicatively, you take it and you multiply it by other endomorphisms you know about and see what happens. You don't know many other endomorphisms, so you can try just to multiply it with itself. That would be pi squared, and you can compute that applying pi twice gives you minus p. And that already tells you that it's a new endomorphism. It's not just scalar multiplication, because no integer has a square which is minus p. So p is something else, pi is something else. And that tells you that if you take the integers and pi, you generate a ring of dimension 2. Okay, so let's try to find a second endomorphism. And looking at this simple equation, you may find that one that sends xy to minus x alpha y. And again, you can ask, is it a new endomorphism? First, is it something else than just a scalar? Second, does it not fall in the ring that was already generated by pi? Well, you can try again to compose iota with itself, and it's a very simple computation to check that it gives you -1. So yeah, it cannot be scalar multiplication. It's a square root of -1. That doesn't immediately tell you that it's not already in the ring generated by pi. So there are several ways to see that it's not. So it's really something new, something that lives outside this two-dimensional ring. One of the ways to do it is to try and compose iota and pi together and see what's happening. And you will find that they anti-commute. Iota pi is equal to minus pi iota. And therefore, the ring these two generate together cannot be a quadratic ring, because quadratic rings are commutative. So these two generate a ring of dimension 4. That already proves that this is supersingular. And we've used the fact that P is 3 mod 4 here in the definition of this iota, where alpha is a square root of -1. The fact that P is 3 mod 4 means that alpha lives in an extension of that field. And it means that it implies that these two will anti-commute. Okay, so we have found this, and we may guess, okay, it has dimension 4. Is it the entire endomorphism ring? And you may be wondering, are we even able to check if we're done? Well, the trick here is to notice that the endomorphism ring is a lattice. It's a geometric structure. It comes with a scalar multiplication, with a scalar product. It comes with a geometry. It comes with a volume. So you can compute the volume of this lattice. And then you have a theorem that tells you what the volume of the endomorphism ring should be. So you compute the volume of that, and you figure that it's something like p squared. And the theorem tells you, oh, the volume of the endomorphism ring is p squared over 4. So you're a factor 4 off. It means that you're not done. But 4 is not so big, and you can do a little exhaustive search and figure that what you're missing are exactly these half elements. Okay. So that is essentially an example of computing the endomorphism ring, but it is a simple one that we know how to do in polynomial time. And the endomorphism ring problem is just the generalization to arbitrary curves. And there are two flavors of that. The endomorphism ring problem is what I actually solved just now. It's, can you find 4 endomorphisms that generate all the others as a lattice? And there is a more abstract variant called max order, which doesn't ask for 4 actual endomorphisms, but just asks for the abstract structure of the ring. More precisely, we know that this endomorphism ring is isomorphic to a subring of a quaternion algebra, BP infinity, which is defined as the unique quaternion algebra ramified at P and infinity, if you know what that means. So we know that the endomorphism ring is isomorphic to a subring of that. And the question is, which one? When you answer this question, you don't actually find any endomorphisms. You just find an algebraic structure. Okay, next, the more classical problem, the isogeny path problem, which may be the one you're first familiar with when you enter isogeny-based cryptography. We define the L isogeny graph. So L is a prime, usually a small prime, L equals 2. The set of vertices of your graph are all the supersingular elliptic curves, and you have finitely many of them. And you have an edge between 2 vertices of your graph, if and only if you have an isogeny of degree L that connects them. So here I would add an isogeny here if they are isogeny. If there exists an isogeny of degree L, I would add an edge here. And you get a graph like that. So it's essentially just a simple L+1 regular graph with a few kinks. You have some multiple edges, some loops. These are rare. Sometimes you're going to have orientation. So you're going to have multiplicities on your edges. And sometimes the multiplicities in the one direction don't match the multiplicities in the other direction. But essentially, it's undirected. And more surprisingly, it is a connected graph. This, I think, it's a very surprising result, given the way it's defined, that you actually get something connected, whatever your choice of L is. It's been strongly connected between any 2 vertices. You have a short path. Okay, so you have a connected graph, and there is an associated path-finding question. And it's the L isogeny path problem. Given 2 supersingular elliptic curves E and F, can you find a path between them? Okay, so that's for the 3 main problems: the L isogeny path problem, the endomorphism ring problem, and the max order problem. How are they related? They actually are all equivalent, but none of the reductions is obvious. However, there is a fairly intuitive idea of why they relate to each other. Even the L isogeny path problem and the endomorphism ring problem, they feel a little bit different. But here I'm trying to convince you that if you have an oracle for one, then you get an algorithm for the second one. Suppose you can solve the L isogeny path problem. Does that help you solve the EndRing problem? So let's see. You have an oracle for L isogeny path, and you're given an endomorphism ring instance. So you're given a curve E, and you're looking for endomorphisms of E. Since you have an oracle for L isogeny path, it makes sense to look at what's happening in the graph. So you look at the graph of L isogenies, and you're going to work in there. First thing you can try to do is walk randomly in this graph to construct a random path. Here in orange, you would end in this random curve F. And a short path will do because your graph is strongly connected. So you're going to end up uniformly distributed fairly quickly. And now you have 2 points E and F. So you can call your oracle for L isogeny path. And that will find you another path from F to E, say this green path here. And the nice thing is that your oracle doesn't know about your orange path. So it will most likely return you a blue path that is completely independent. So now you have found a loop. You have found a path that starts from E, goes through F, and goes back to E. And that is an endomorphism. And since the green path and the orange path are independent, you can assume that one is not just backtracking. You're not just going to F and then doing the reverse path, because that would just be a scalar multiplication. So that seems to give you a non-trivial endomorphism. So you could just say, oh, I found an endomorphism. I add it to my collection, and I repeat that, generating a new random path from E to some random curve and calling my oracle again. I do that a few times. I find a bunch of endomorphisms, and I pray that the ones I find generate everything. So that seems to indicate that indeed EndRing reduces to L isogeny path. Unfortunately, this is all very heuristic, and I'm not sure anyone wrote down a proof that that actually works. It might not be feasible, I don't know. Because nothing guarantees, even though the two paths are independent, nothing guarantees that you're not just gonna always end up with a cycle that falls in a subring. And then you're never gonna generate the whole endomorphism ring. However, the three problems are still equivalent. The reductions are just different than what I just said. And now that's known under the generalized Riemann hypothesis, and that's Fox 2021 paper. And before that, there were heuristic reductions between all three problems by these two papers. Okay, so I'm going to try and give you a little idea of how the actual reductions work. And for that, I need to say a little bit more about the max order problem. Main observation is that we have two worlds and a correspondence between the two worlds, and that's known as the Enring correspondence. I'm going to talk about the isogeny world on one side and the quaternion world on the other side. In the isogeny world, the main objects are the supersingular curves E over some given finite field, up to isomorphism, so you only have finitely many objects. And on the quaternion world, your objects will be maximal orders in my quaternion algebra BP infinity. So this is just a four-dimensional algebra, and maximal orders in there are simply subrings that are discrete and not contained in any other subring that is discrete. And again, if you look at maximal orders up to isomorphism, you also have finitely many of them. And now, I mentioned already that if you take a supersingular elliptic curve, its endomorphism ring is isomorphic to one of these orders. So that already gives you a map from this world to this world. And in fact, it's essentially a bijection. If you give me a maximal order, there is a corresponding elliptic curve here whose endomorphism ring is isomorphic to that order. So the Enring correspondence is a bijection between these two worlds. It's actually more than that. It's an equivalence of categories, meaning that it also preserves morphisms. So what are the morphisms? The choice is pretty obvious on the side of isogenies, of the isogeny world. Well, it's isogenies. Morphisms between your elliptic curves are isogenies between the elliptic curves. But the morphisms, in a category theoretic sense, on the quaternion world, are not just ring morphisms between orders. They are ideals. So how does that make sense? How can we see that ideals connect orders? Here, an isogeny connects the source to its target. Here, you have ideals in a non-commutative world, meaning that you can be an ideal on the left or an ideal on the right. Any ideal will be an ideal on the left in some order and an ideal on the right in some other order. In that case, I call that an OO prime ideal. And we can think of these ideals as connecting O and O prime in the same way as an isogeny connects the source to its target. And this correspondence actually preserves a lot of very nice properties. To every isogeny, you have a corresponding ideal, and the degree of the isogeny gives you the norm of the ideal. I have a lot of very nice things here. And max order is simply the problem of translating from the first world to the second world. If I give you an elliptic curve, can you find the corresponding maximal order? Going in the other direction is always doable in polynomial time. Okay, so we have these two worlds that are actually so similar. If we have a computational problem in one, we can ask the analog question in the other. For instance, the n-isogeny path problem. Given two elliptic curves E and E prime, can you find an isogeny from E to E prime of degree n? Well, there is a corresponding n-quaternion path problem. You're given two orders O and O prime. Can you find an OO prime ideal I of norm n? It's just the same problem from a different perspective. Now, the first one we suspect is hard. The second one, well, you may know that it is actually solvable in polynomial time. Heuristically, that is done by the KLPT algorithm, or Coel-Lauter-Petit-Antignol. Rigorously, we know how to do that. Well, not completely rigorously. We need still to assume the generalized Riemann hypothesis. If you assume that, we know how to solve that in polynomial time. So how does that relate to reductions? Well, suppose you have an instance of the n-isogeny path problem, and you have an oracle for max order. Given this instance, you call max order on E and E prime, it gives you two orders O and O prime. You can solve this problem, and then you can go back, because going back is always easy. So if you have an oracle for max order, you can solve an isogeny path, and that is the reduction. Okay. Sorry. Must n be smooth? Well, you will need to, you will need to find, to be able to represent your isogeny in a way that allows efficient evaluation on points, indeed. So n being smooth is one solution, yes. But you may imagine other contexts where you can represent isogenies that don't have smooth degrees in a way that still allows polynomial time evaluation. Sorry? Exactly, yes. Okay. So next I'm going to talk about orientations in order to be able to talk about these other problems that I presented at the beginning, the vectorization problem, for instance. So we have these three problems that are equivalent, and we would hope for that to be the foundation of isogeny-based cryptography. We want crypto systems that are as hard as these problems. Unfortunately, while we often have reductions from breaking crypto systems to these problems, the converse is only rarely true. And the reason is that it's usually much easier to relate crypto systems to other problems like vectorization or oriented Diffie-Hellman or previously CSSI. Vectorization orientations will allow to discuss these problems. Okay, so what is an orientation? As I said, the endomorphism ring is a ring of dimension 4. But now if you take any endomorphism alpha that is not just a scalar, then it generates a subring that has dimension 2. We call that a quadratic ring. It's always a ring of this form, the polynomial ring over Z quotiented by a quadratic polynomial. Okay, so the ring of integers, even though it has dimension 4, contains many subrings of dimension 2. You can take the problem the other way around. If you start with a quadratic ring, how many ways do you have to embed this ring inside the endomorphism ring? Any such embedding would be an orientation. So an orientation is just a map from your quadratic ring inside the endomorphism ring of the curve. Then O-oriented curve is such a pair. And the set of all O-oriented curves, we always fix the characteristic P of the field, is written LO of P. So that's a notion that was introduced by Colo and Coel in order to define a key exchange protocol. And the reason we care about that is that it allows to define a group action. We have a group action on this set of supersingular oriented elliptic curves. I'm not going to define precisely how this group action works, but I'm going to tell you what is the group acting. It is simply the class group of the quadratic ring. Any quadratic ring comes with this finite abelian group, the ideal class group of the ring. And it acts on the set of all oriented elliptic curves. I'm going to write this section with a star. And in the rest of the talk, I'm going to abuse notation a little bit and say that E is an oriented curve, even though properly speaking, it should be E, a pair E iota. So when I say that E is oriented, I imply that there is an orientation on E. The fact that this is a group action means we have two properties, the compatibility between this star operator and the multiplication in the group. So if I apply alpha and beta, alpha and B, so A and B, it's the same as applying the product AB. And there is an identity that acts trivially. Okay. The main reason why you may already be familiar with these notions and this action and orientations is probably because of CSIDH. CSIDH has an orientation in disguise, and this is the Frobenius orientation. If we fix SS of FP to be the set of supersingular curves defined over FP, the prime fields, as opposed to FP squared, then any curve in there has a Frobenius endomorphism, and it satisfies pi squared is equal to minus p. So pi squared equals minus p means, in some sense, that pi is a square root of minus p. So you can look at this ring, z adjoint square root minus p, and any curve E in that set has a z adjoint square root minus p orientation, which is simply the embedding that sends the square root of minus p to the Frobenius. So it's pretty clear that anything in there has a z adjoint square root minus p orientation. What's a bit less obvious, but still quite simple to see, is that if you have a z adjoint square root minus p orientation, then you are defined over fp. So being oriented by this or being part of the set are actually the same thing. They are synonyms. So the class group of this quadratic ring acts on SS of fp. And that gives you CSIDH. So I'm not going to detail that because I'm sure you're all very familiar with it. But the point I'm trying to make here is that you could replace in CSIDH the action of z adjoint square root minus p by any other order O. And you would get a protocol that in theory would work. The main difficulty would be how to generate ideals whose action can efficiently be evaluated. And the context of CSIDH is very favorable to that efficient computation. So this protocol comes with an associated computational problem, the CSIDH problem. You're given a reference elliptic curve E0. You're given A star E0 and you're given B star E0. Can you find A B star E0? And that's a problem that looks very much like the classic Diffie-Hellman problem. And in fact, D and H here stand for Diffie-Hellman for that reason. Okay. So what is vectorization and how does it relate to that problem? Here's the more general version of the CSIDH problem. It's just the same problem where you allow arbitrary orientations instead of just the Frobenius orientation. You're given E, A star E, B star E, can you compute A, B star E? And the vectorization problem is the following. You're given E and A star E, can you find A? So the vectorization problem is to this O Diffie-Hellman problem precisely what the discrete logarithm problem is to standard Diffie-Hellman. And how do they relate? Well, it seems pretty clear that at least, okay, classically, if you can solve discrete logarithms, you can solve Diffie-Hellman. Okay, you hope that the same is true here, and it's true. Evidently, O Diffie-Hellman reduces to O vectorization. If you can recover A, you have an algorithm that given E and A star E finds A. So here you use these two, you find A, you apply the action of A on that, and you find that. Sounds clear enough? There is actually a subtlety here, which is this algorithm will find you A, but applying the action of A may not be so easy. But we can circumvent this issue and actually prove that there is a polynomial time reduction from one to the other. What about the other direction? If you can solve Diffie-Hellman, can you solve vectorization? It's much less obvious because Diffie-Hellman gives you in your output, well, a curve, an oriented curve. It doesn't give you a group element. So what can you do with that? Well, it's much less obvious, but you actually do have a reduction. The fact that it's less obvious is translated in the fact that you need a quantum computer. There is a quantum polynomial time reduction from vectorization to Diffie-Hellman. So that's again, that's proven in a Eurogroup 2022 article, but there is an earlier work that proves a sub-exponential reduction that is very similar. And the sub-exponential part precisely comes from the very same subtlety that I emphasize in this asterisk here, which is when you're given an A, it's not obvious how to apply the action of A. Okay, so here are our two problems, O Diffie-Hellman and O vectorization. I hope I convinced you that we care about them because this one is essentially equivalent to breaking CSIDH when properly instantiated. And we have an obvious reduction from Diffie-Hellman to vectorization and a quantum reduction in the other direction. I spent the first half of the talk trying to convince you that the problem we actually care about is the endomorphism ring problem. It should be the foundation of isogeny-based cryptography. And this really doesn't look like endomorphism rings. So how do we relate this to endomorphism rings? So first, let's introduce an oriented variant of the endomorphism ring problem as a first step. It would be the same problem. You're given a curve, can you compute this and its endomorphism ring? But now I give you an oriented curve, not just a curve. And that gives you the EndRing problem. It is a priori simpler because it is the same problem with more information in the inputs. I just give you an orientation in addition to a curve, so maybe you can use that to solve the problem faster. So here's again the vectorization problem, and it really seems like a different flavor of problem. Here you're looking for a basis of a lattice, and here you're looking to invert a group action. But it turns out they actually are equivalent with two caveats. The first is that you need to assume the generalized Riemann hypothesis, which is usually fine. And the other is that you need to know the factorization of the discriminant of your order. Is that fine? Well, I guess it's fine for two reasons. The first is that for all known instantiations, at least in the case of CSIDH and other variants, the discriminant is essentially one big prime number, so its factorization is trivial. The second reason is that we care about quantum security anyway, so if you really care about having a difficult to factor discriminant here, just add a quantum computer and you get a polynomial time quantum reduction. Okay, so again, that's in the same Eurogroup 2022 article. And again, there is an earlier work that is very similar that proves sub-exponential reductions in the case of the CSIDH setting. So for this orientation, from O vectorization to O EndRing. So back to the picture, there is this problem O EndRing, which turns out to be equivalent to the other problems. And how does that relate to the standard endomorphism ring problem? Well, there is an obvious reduction from O EndRing to EndRing, because if you can solve EndRing, you can solve O EndRing by just forgetting about the additional information I give you. Forget about the orientation. In the other direction, it's less trivial. I need to restrict the EndRing problem to things that are at least O-orientable. I don't give you orientations, but I promise you that there is one. Then we do have a reduction in the other direction in the CSIDH setting. So when O is 0 square root minus B. So there we are finding ourselves in a very nice situation where we have arrows in both directions straight from EndRing to breaking CSIDH, where the only difference between this EndRing problem and the standard one is that I'm restricted here to curves defined over FP. So CSIDH is provably as secure as breaking the endomorphism ring for curves defined over FP. So we care about this problem here because it's equivalent to isogeny path, which relates to many other crypto systems, but not quite all of them. And the annoying thing here is that we don't have any notion of a group action here, which turned out to be very practical there to build crypto systems and to analyze them. So question is, there some harder variant of vectorization that maybe will be equivalent to the endomorphism ring problem? So going in that direction was the Uber problem. The O-Uber problem is essentially the same as the vectorization problem, except I don't give you one of the orientations in the input. I give you an O-oriented curve, E, and an O-orientable curve, F. And can you find a group element A that sends E to F? The only difference with vectorization is that in vectorization, I would give you an orientation for F, and here I don't give it to you. So that makes the problem harder. You have less information in the input. That problem was introduced in that paper with many authors. And the purpose of this problem is that it's very easy to reduce the security of crypto systems to this problem. And it was proven in the same paper that CSIDH, OSIDH, SIDH, and Shitta all reduced to O-Uber. So it serves as a very good upper bound for the security of crypto systems. So how does that relate to the endomorphism ring problem? Well, again, I need another variant of the endomorphism ring problem called O-EndRing star, which is, again, the problem of, I give you a curve, can you find its endomorphism ring? And now I promise you the input is O-orientable, and I'm asking more in the output. I'm asking, can you find the orientation that I didn't want to give you? And again, these problems are actually equivalent with the same caveats as previously. You need to know the factorization of the discriminant, and you need to assume the generalized Riemann hypothesis. Okay, so back to the big picture, we now have this O-Uber problem here, equivalent to the O-EndRing star problem, and they are equivalent. And how do they relate to the standard endomorphism ring problem? Well, there is a clear reduction from the standard EndRing problem to O-EndRing star problem, because in O-EndRing star problem, I'm asking the same question, plus I also ask you to find an orientation. If you're able to do that, you can just return the first part of your answer and don't return your orientation, and then you've solved EndRing. In the other direction, well, again, the question is more difficult and we only have partial answers to that. At least it's known that you can go from O-EndRing star, to EndRing when the discriminant of O is not too big. So when the square discriminant is smaller than 4p. For large discriminants, we don't know if these problems are actually different or if this is actually as hard as that. So let's clean this up a little bit and organize that into categories where we have first endomorphism ring problems, then group action related problems, and then crypto systems. We know that breaking any isogeny-based schemes reduces to these two problems. And the question is, what can we prove in the other direction? What kind of security proofs do we have? What kind of protocols can we build that are provably secure if this is hard? Because this is the hardest line. It's the problem that everything reduces to. We know how to build one-way functions from that. So that's already something. From one-way functions, we get signatures. But do we have public key encryption? Well, we don't know. We still don't have an isogeny-based scheme, public key encryption scheme, that is provably as secure as O-EndRing star, O-Uber, or even EndRing. That is a very nice open question. Maybe it's infeasible. What we do have, however, is a public key encryption scheme at this level, and that's simply CSIDH. So if that problem is hard, we have PKE. And I guess that concludes my talk. Yes, thank you for your attention.
So thanks a lot, Benjamin, for this nice overview. Are there questions? Yeah.
Yeah, so my question is related on, so there was this slide between elliptic curves and quaternion algebras.
Okay.
Yeah, it's fine. I think
Okay.
you don't have to go back. So can you actually for any n, can you actually find a connecting ideal of norm n? Or isn't this, do you need some more flexibility? Like in
We need
isogeny
n to be
class,
big enough.
if n is big enough, right?
Yeah.
Ah, okay. So if n is, so suppose when it's very, very big, right? So much bigger than expected pass.
Big enough so KLPT works.
Yeah, got it. That's prime, right?
Not prime. What do you mean? Yes. Okay. Yes. It can be near prime. It can be a prime times something smooth. It could be, yeah, true.
But it has to be bigger than the smallest expected path lengths at the moment.
Yeah.
Okay.
Can you say that again? Yeah. The correspondence is a bijection that preserves, well, the degree turns into the norm. So if you have an isogeny of a given degree, you have an ideal of the given norm, yes. But it doesn't mean you can efficiently compute it. That will depend on the cases. Yes, possibly, yes. Although for collision resistance, you need a trusted setup. You need an elliptic curve of a known endomorphism ring, right? So we don't, yeah. You would need, maybe you need more assumptions than just the endomorphism ring problem if you need also another protocol that generates a curve of a known endomorphism ring.
More questions? Yes.
So you hinted at this one endomorphism ring problem for ski sign, and it looks similar to O EndRing star, because then you only need one more to get the whole endomorphism ring. Is it similar, do you think?
Well, in O EndRing star, you still need to find the entire endomorphism ring. O EndRing star asks, can you find all the endomorphisms? And can you find an orientation, which is, can you find a subring of the endomorphism ring that has the correct shape?
Yeah, I don't know which one to point at, but it looks similar to finding one more compared to having an orientation, I guess.
It feels similar to, I think it feels similar to this arrow, because no, maybe not, but I'm a bit bothered by this arrow because it feels like every time you have the endomorphism ring, everything is easy. But now it feels like having the endomorphism ring is not sufficient to find the orientation you're looking for.
Okay. Unknown then for the moment, I guess.
Yeah, for the moment, one end is heuristically equivalent to endomorphism ring.
Okay.
I guess the argument is the usual one. Suppose you have an algorithm that finds one endomorphism, and I'm asking you find them all. Well, call it once, you find one endomorphism. Then if you call it again on the same curve, well, you're going to find the same thing most likely if your algorithm is not properly randomized. You can do a little random walk, find an endomorphism there, bring it back, and hope that bringing enough endomorphisms will give you everything. But again, there is this problem that maybe you're always going to find something that falls in a subring. So yeah, so far one end seems simpler than EndRing.
Okay, I'll watch that space.
There was another question there. Yeah, can you reach that?
Hi, thanks. What about some more bizarre problems like I choose a quadratic order and take some elliptic curve. Is it orientable by my order? Where would this problem be in your picture?
So it's just a decision problem. We're asking to find the endomorphism, the orientation. Well, I don't know. These are not decision problems. The decisional Uber problem? Yeah, actually, yeah, it is. Yes, it's the decisional Uber problem.
Thanks.
The orientation theories you stated are quite general for general quadratic orders that embeds in BP infinity, right? But in practice, I've been only seeing the order that's associated to C side and maybe O side. Do you see the general quadratic orders being used to build protocols?
Yeah, it's possible to build protocols based on arbitrary orders. There's the technical question of then if you choose another order, can you make the evaluation of the group action efficient? And well, that requires a lot of work and probably won't get something as efficient as C side, but maybe get close.
Okay, thanks.
Thanks. More questions? Yes. It's a bit like going in the supermarket trying to find the most efficient.
Yeah, so in your reduction from the Diffie-Hellman to the vectorization problem, you mentioned that at face value, this runs into this classical issue that we don't know how to evaluate the action of a given ideal in polynomial time, unless it's smooth or something. And you were able to work around this for that reduction, but is it correct that you still don't know how to do that just as an isolated task, given an ideal, figure out its action without like in polynomial time?
Yeah, that's the case. We don't know how to do that without actually. The key is that if you know the ideal and the endomorphism ring, then you can evaluate the action of the ideal efficiently. So if you give me a curve without the endomorphism ring and you give me an ideal, I don't know how to evaluate its action efficiently.
That's comforting to know.
How do you describe the ideal? Well, just as an ideal in a quadratic order. So it's a lattice, right? Your quadratic order is Z adjoint some generator, and your ideal is a subring generated by two elements. So it wouldn't be represented as an endomorphism. It would be represented as an algebraic integer. Then you are given your orientation. So I don't know if I can write on the board, people on Zoom won't see it, but you are given an orientation, and computationally, that means you are given a quadratic ring, so just a polynomial, and you are given an endomorphism that corresponds to an element, preferably a generator of your ring. So you have a ring and an endomorphism that is the image through your orientation of a generator of the ring. Now, if I give you any algebraic element in your ring, it's a linear combination of, well, an integer and your generator. So you can represent your endomorphism as a linear combination of, well, the identity, well, scalar multiplication, and the endomorphism that you're given as input that represents your orientation.
Okay, more questions? Yes.
Yeah, so in the beginning of the talk, you mentioned twice that you think it's surprising that these isogeny graphs are connected and strongly connected. Can you explain why this is surprising?
Oh, just from the very definition, you're saying, oh, I'm just going to look at elliptic curves that are super singular, and then I'm going to restrict my morphisms to things of degree 2. And there's no obvious reason to think that that's sufficient to reach everything. That's not even true for ordinary curves, for instance. And then suddenly in the super singular case, everything is reachable, and everything is reachable fast. I don't mean anything deeper than that. It's just, I'm surprised.
Thank you.
More questions? If not, let's thank Benjamin again.